This tutorial is the solutions for your Chapter 3 Mixed FIP quiz. This has solving and resolving vectors, non-perpendicular vectors, projectile motion launched on the horizontal, and projectile motion launched at an angle. We'll start off with number 1. Two friends make a break for it and race to the PA state line. First friend takes off going at 25.7 meters per second, but heading 27 north of east. If you want to beat your friend to the state line, what speed will you have to match? Well, what we're looking for here is actually just the x component of the first person's velocity. So this velocity is 25.7 meters per second. The angle is here, therefore this is the adjacent angle. So cosine of theta equals v sub x over v. Cosine theta times v will give us our v sub x. Cosine of 27 degrees times 25.7 meters per second will give us v sub x. Our raw value is 22.8988, etc. meters per second. So, thinking about this in real-world terms, since what we want to do is beat the other party to that vertical line, the speed to beat with sig figs would be 23 meters per second. So the velocity of the friend must be greater than 23 meters per second if she's going to beat her friend to the state line. Okay, next. This is one of those kicked, flicked, and pushed problems where we have an object in projectile motion but being launched on the horizontal. So someone has delivered a care package to you via plane. It's shoved out of a low-flying plane 6 meters above the ground and travels 8.2 meters horizontally before hitting the ground. What we want to know was the package's initial velocity. So we've listed our variables on the x and y axis. Since v initial on the y-axis is 0, we know that all the velocity that this object has initially is on the x-axis. That's our total initial velocity. Delta x is 8.2 meters. Delta t we can create an expression for using delta x divided by v sub x. On the y-axis, we already mentioned that our initial velocity is 0. Our acceleration is negative 9.81 meters per second squared, as usual, and our delta y is negative 6.0 meters. We'll create an expression that includes time to bridge the two axes, using factors on the y-axis. There we have it. Of course, since VIY is 0, this immediately disappears. And we're left with the much neater, much simpler expression that looks something like this. Yay! We now have a place that we can plug in the expression that we created for time on the x-axis. Once we plug in our expression for time, we have delta y equals 1/2 a times the quantity delta x over vi cosine theta, quantity squared. Now, we'll do a little bit of algebraic magic, because of course, in the end, we're solving for vi. Okay, so we now have delta y equals a delta x squared over 2 vi squared cosine squared theta. Wait, did I already say that? I don't know. Anyway, our next step is working towards isolating vi. No matter how you do it algebraically, you want this vi, of course, to end up over here. So you can multiply both sides by vi, or multiply both sides by 2 cosine squared theta. Okay, we've got vi squared isolated, so of course to solve for vi, which is vix, we just take the square root of this, which eliminates that exponent. Alright, time to plug in values. Please pardon me, there is no cosine theta. All the initial velocity is on the x-axis. That's just vix. Whoops. Okay, we'll go from there. So VI is equal to the square root of negative 9.81 meters per second squared times our delta x, 8.2 meters squared, divided by the quantity 2 times our delta y, 2 times negative 6 meters. That gives us a raw value for VI, and I really should say VIX, or V sub x, of 7.414087, it just keeps going, meters per second. So with sig figs, we get a value for Vx of 7.4 meters per second. Okay, up next. Okay, for number 3, you're being chased toward a cliff over a deep lava-filled chasm by a vicious ankle-chewing, whatever. The chasm's 3 meters wide, and the cliff on the other side is 2 meters lower than the cliff off of which you are leaping. If you make your leap at a 15-degree angle, what velocity will be required to make the jump? If top human speed is 10 meters per second, can you make it? So this is similar to the problem we've had before of someone leaping off one roof and us wondering if they can make it at a given velocity. Except the twist here is that we're asked for the velocity needed to make the jump. So what we're really thinking about is that on this projectile course, for every point on the y-axis, there's a corresponding point on the x-axis. And what we want to know is at this point, at 3 meters on the x-axis, where on the y-axis are you? In other words, can you make it? So we'll set our value for delta y to negative 2 meters, which will give us the velocity required to just make the edge of the cliff. As usual, we've listed our variables on the x and y axis with our Vix and Viy expressed using the common trig functions. Cosine theta Vi equals Vix, sine theta Vi equals Viy. Our delta x is 3 meters, and our delta y is negative 2 meters. We've built an expression for time on the x-axis. Delta x over Vix is equal to time. And now we're going to use an equation on the y-axis that will allow us a substitution to tie together our two axes. The best candidate's still our old friend. Delta y equals Viy delta t plus 1/2 a delta t squared. We'll go ahead and do all of our expression substitutions in one handy step. Delta y equals Vi sine theta times the quantity delta x over Vi cosine theta plus 1/2 a times the quantity delta x squared over Vi squared cosine squared theta. Alright, now let's do some more algebraic magic and get rid of our Vi's, and we'll convert that sine divided by cosine into a tangent function. While we're at it, we might as well distribute everything outside the parentheses across the fraction. Okay, remember we're working to isolate this Vi, so we're going to start by moving this across the equal sign. We now have delta y minus tangent theta delta x equals a delta x squared over 2 Vi squared cosine squared theta. Whew, almost done. Again, two ways to handle it algebraically. You can multiply both sides by by Vi squared, or you can move the 2 cosine squared theta to the other side and then swap those out. In either case, what you end up with next is this. Vi squared is equal to a delta x squared over 2 cosine squared theta times the quantity delta y minus tangent theta delta x. Close parentheses. Now we take a square root and we're done. Alright, we're ready to plug in our values and get a raw answer. Okay, that's a lot of nested functions, so it's a good place to be really super careful with your calculator entry. Okay, we get a raw answer for Vi of 4.107899236 meters per second. When we sig fig that, we get a Vi of 4.1 meters per second. So yes, you can make it, and you can make it with speed to spare. Moving on to number 4. Okay, we're told that the first day of deer season, you've traveled 1.48 kilometers at 34 degrees south of west when you get a deer. You then have to follow that deer for 0.85 kilometers at 52 north of east. So the angle is in here. Ooh, this is a tough one. So to see the triangles presented by each part clearly. I'm going to draw them in color first, and then I'm going to pull them out of the main picture. That's one of the big challenges with this, is the triangles actually superimpose on one another. For our first triangle, we've got an x displacement, delta x1, there, and a y displacement, delta y1, right there. Okay, now to draw in the second triangle. Okay, so there's our second triangle, very tiny and completely contained inside the first one, and that's got a delta x2 that's here and a delta y2 that's here. Notice that the directions on the delta x2 and the delta y2 are in opposition to delta x1 and delta y1. So the thing to remember is what you're looking for overall, of course. Well, what you're looking for is the resultant. So your resultant x will be the difference between these two x displacements. In other words, it'll be that. And the delta y resultant will be the difference between your two y resultants, something like that. This is a long, skinny, flat triangle. So your overall resultant here is going to look like that.